Next speaker, from Barbara, I learned that plants also sense and move, and this gave inspiration to very cool robots. But in the newest work, she does not want to harm those plants, and she will present EcoRobots. So please, Barbara.
Thank you, Bram. Thank you. And thank you also, Stefano and Tamime, for the invitation. I'm very pleased to be here. And I would like to take my time to share with you some of the activities we are doing in the field of bio-inspired soft robotics, and more recently in developing EcoRobots as a soft machine for sustainable environmental applications. But before delving into the topic, I would like to ask you to take a moment and think back to the first time that you heard the word sustainability. So can you remember if this word was introduced to you as a new concept, or you are under 30, and so you are part of the first generation sustainability natives? Okay, let me later in the corner. So, well, I remember that I was in a class of an international master program on environmental management when I was introduced to this word, sustainability, around 10 years after its official introduction by Gro Harlem Brundtland, the first woman prime minister of Norway, in her 1987 Our Common Future report for the United Nations, where she defined sustainable development as the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Simple, yet a powerful definition, and why it's still challenging to implement such a scenario in reality, at that time for me was like an epiphany, was really inspired by this concept I tried to implement in my research. So sustainability is a very urgent and important topic, but what about technology? So why technology advances? Most of the current technological solutions are energy demanding, and they produce 1 million tons per year of electronic waste, so what is called e-waste. So a change is needed, and the question is what we can do as technology developers to help in achieving a better scenario. So recently, together with Cecilia Lasky, we have proposed this concept of cycle life in robotics, which envisions robots designed to operate alongside humans and other living beings without causing any damage. They can also protect the natural resources instead of just exploiting them. And at the end of the life cycle, they are reusable or biodegradable. But before making robotics greener, there are several technological and scientific challenges that we have to address. First of all, new materials that are more sustainable, so they show multifunctional properties, self-healing, and here there is Bram, it's an expert in this. Biodegradability, we need to enhance the sensing capabilities of our robots, also including chemical sensors. We need new electronics, battery, but very important, we need new tools for design and energy use optimization. And this is why we are taking inspiration from nature, because this is exactly the traits that allow living organisms to operate and adapt to dynamically changing conditions in real scenarios. So we are trying to imitate the adaptation, the plasticity of living organisms in our robot. So I would like to share what we are doing in this direction very briefly. First of all, we are developing robots that are intrinsically safe because they are taking inspiration from cephalopods mainly, like an octopus. So we started several years ago investigating the morphology, the distributed sensing and intelligence of this animal to develop a soft continuum arm with suckers to collect, retrieve, and manipulate objects in delicate environment, like in this case it was an industrial project for retrieving objects in wells with a high pressure. Recently, also, we start to investigate earthworms, very soft animals, but they can generate pressure to penetrate in soil. They work like an hydraulic skeleton because they have a muscle and liquid inside the body, and they push the head in the soil. And so we have developed this soft, compliant robot. As Bram say, we are investigating plants and their capability to move by growing. In fact, the plants are defined as sessile organisms, so they stay, the terrestrial plants, they stay in the point where they germinate. And so in order to move, they have to grow. And they do that by adding new cells, both in the root and the shoots, at the tip. So there are stem cells that divide continuously, then differentiate, and the only part that is pushed in the environment, for example, in the soil, also in very hard soil, is the tip. And this way, they reduce friction, and also they reduce the energy for implementing such a movement. And so we transfer this concept in a robot that is able to move by growing, miniaturizing a 3D printed machine inside the head. So using thermoplastic material, the robot layer by layer is able to create its own body, and the direction growing is provided by the sensors and the behavior imitating plants, so they grow following or escaping from environmental stimuli. And so the same for climbing plants, so they can find the support without a brain, without eyes, and we are implementing the same behavior in our robot. Also, recently we discovered that plants can generate energy by triboelectric effect. By chance, we discovered, so when soft leaves, artificial leaves, mechanically touches natural leaves, so they can generate this interaction moved by wind, generated by triboelectric effect charges, positive and negative, that can be used to power LEDs, sensors in situ. So it's a really green energy. But today I would like to focus more on, sorry, this was the video. And I would like to focus mainly on the movement that are called passive in plants, since there is no metabolism. These are typically fruits that transport the seed into the environment. So they are dead structures, but they continue to move thanks to the interaction of the materials in the cell wall with external factors like humidity, temperature variation, and of course wind. So the secret is in the fact that there is a cellulose-based materials that absorb and dissolve water, and lignin-based material that, depending on the angle that they generate, they activate movements like calling, uncalling, flying, and so on. And these are the perfect models to develop biodegradable soft robots that move into the environment, that can drill into the soil, that can fly. They are covered with nanoparticles that are also biodegradable, and are sensitive to some elements, like in this case, elemental mercury, CO2, temperature, humidity, and can emit fluorescence when are excited by laser beams on board the drones. This fluorescence is also read by LiDAR techniques on board the drones, and so on the basis of the intensity of the fluorescence, we can understand the concentration of such an element. And we skip totally electronics and batteries, so we can release hundreds of these robots without affecting the environment. This is the approach. So we started from biology. So we investigated the arrangement of the materials, as I said, so using different techniques, so in this case, histology. And you can see the secret. So in blue, this is the species Pelargonium, that is a drilling seed. So in blue, there are cellulose-based materials, as I said, that are the sensitive element. So they absorb and dissolve water. And then the microfiber or lignin that play the movement. To demonstrate such a concept, we have developed several mock-ups in softer materials, like the PCl and the PO, that is a sensitive material to polyethylene oxide that is sensitive to humidity variation. And the only aspect that we change is the angle of these fibers deposited by electrospinning machines. And what we obtain is a completely different movement. So in the same condition of a humidity variation, same materials, the only variable is the angle of these fibers, we can generate bending, torsion, drilling, coiling, and so on. So completely different movements. So we play with this, and we develop different soft robots that can coil and uncoil to penetrate in soil. So there is no control. The control is in the design. And then in the fact that the robot can exploit the energy from the environment and release the energy in the materials, like the natural system. And so we can detect different parameters in this way. Not only drilling, also flying. This is the case of the Acer, the Samara. The approach is the same that I explained before. We start from the arrangement of the material in biology, and then we transfer in artificial system. We cover with nanoparticles sensitive to this element, and then we can read the fluorescence by using drones, so without, as I said, affecting the environment. And very recently, we also developed a system, biohybrid systems, for reforestation, not only for monitoring, by taking natural elements from avena seed, because they are really fast in reply to humidity variation into the environment. So we extrapolated the tails of the avena, and then we combined with a capsule made of biodegradable materials. We fill the capsule, starting from the natural design, with seeds of different species relevant for the reforestation. And then we release by using drones, and we can use such a kind of soft biodegradable system also for reforestation and monitoring. And to conclude, so our goal is to develop these EcoRobots that are fully integrated in this approach that is called a One Health approach, recently re-emphasized by the United Nations and other international organizations during the COVID-19 pandemic, to reinforce this point. So health of humans, animal, and ecosystems are closely interlinked. So our health depends on the quality of the environment, the food, and so on. And robotics can help to improve the knowledge of humans on the phenomena that occurs in natural ecosystems. And with this, I would like to thank my colleagues that work with me on these topics, and all of you for your kind attention. Thank you so much.
Are there questions? I think yeah, there's a question.
Yeah, it was quite convincing. So I need your quick comment. What is the role of raster angle? Like you have taken 0 degree, 30 and 45. So which one is most stronger in terms of elasticity?
So of course, we use the 45 because the expected movement is a coiling, as I said, and is exactly the same angle, of course, that use also the natural system, so the pelargonium, but also other drilling species. And so this is exactly the most it's not just it's not only for energy, but it's also because that angle generates the drilling. That is exactly what is needed for the natural system, but also for our system to penetrate into the soil. And so it's a combination, and the energy is stored in the materials in all this system, also in our system, and then is released when the system interacts with the external environment. So the angle is more important for generating movements more than, there is not an angle that generates more energy, but is for generating the movement.
All right, thank you.
Thank you.